sound on?
Hello, everyone.
That's a yes.
Another day, another class, and we've been covering the quantum world, especially from the point of view of quantum mechanics. But we do compare it a little bit every now and then against the rope model.
Every now and then, yeah, like once a month, we bring up the real science.
Well, we have to look at what is.
Do we? That was a question I had for you last week or yesterday.
Well, we do. You kind of have to tear it about. You have to
would you be presenting the quantum model if the rope hypothesis were already the mainstream theory?
Someone would. Probably.
Well, with you, that's the question.
Oh, no. You got to present it. You got to present it because, like someone once told me, you first have to destroy what is.
Yeah, but the question is, if the rope hypothesis were already mainstream theory, would you ever talk about the quantum model?
Well, yeah, it's like saying, would I talk about the ether only maybe from a historical point of view, like that it was the fifth element, we had these other four elements, and you say, well, do we need to talk about that? Well, yeah, only in a historical context so that you can put it in a proper context again, so in that sense you would. You probably say, look, this is what people used to believe in. Ptolemaic universe we went over the other day to start the atomic structure. That's how they believed it was. Ptolemaic, why? Because they had all these epicycles and every planet had to revolve around some kind of epicycle except us, because we were the center of the universe. Like obviously the earth didn't move,
like a patchwork theory.
Yeah, you kind of need to relate to that to make some sense. Maybe it makes some sense of how we progressed from that form of thinking to where we are today, right?
Yeah, but it's nice to know, but at this point we're learning more about what isn't than what is.
And one of the reasons you need to know that or need to relate to that is that when you read out there, if you go into science and technology anywhere, like you go to science and technology on YouTube or Facebook or whatever, what are you going to find? You're going to find quantum, you're going to find black holes, you're going to find dark matter, Big Bang, Higgs fields. That's what they talk about. That's what these people do. That's how they make their big bucks. So the people working at CERN, what are they smashing? Well, they're certainly not smashing ropes, or at least they don't think they are. They're smashing particles and so you need to know, well, what do you mean by particle? And the guy said, well, it's an equation. Oh, okay, you're smashing equations. Yeah, and all these variables just pop out. Okay, fine. So you kind of have to understand what they're doing, because that's what you're going to find out there. You're not going to find a rope model out there, being discussed by the majority of the population.
Yeah, but my point is, you seem more interested in tearing down or debunking mainstream theories than teaching your own.
Let me tell you, the issue there is that the mainstream theory is quite complex.
You're telling me
it's a Ptolemaic system. It's over 200 particles now. We're 200 and counting. They're inventing more and more particles. Like we said the other day, we're not converging upon the particle that makes up everything. It's quite the opposite. It's like we're diverging. Getting farther and farther away from the single particle. That's one issue. The other one is that maybe they are converging. You saw my article, got over 2,000 hits now in Quora, and what does the article say? Is that everything, what underlies everything? And it's fields. Fields. That's the big word now. Fields. And you have quantum field theory. And so, what is a particle made out of? It's made out of a field. And so now you have to find out, okay, what do you mean by field? And you kind of need to cover that base, because that's what you'll find out there. And if you don't cover it, people say, well, you're out of touch. We don't deal with, what was it the other day? We said, we had the standard atoms. What is an atom? An atom is a little particle, proton, and it's orbited by this electron. And when you go to the table of the elements, the periodic table, that's what you thought you were looking at. Now you have, these exotic atoms, these exotic elements. Now you have a hydrogen atom, and it's a proton orbited by a muon or a pion or whatever. Yeah, it's heavier than an electron. It's not exactly. No, in fact, they say that the muon decays into a pion, which eventually decays into an electron. So the electron is part of a muon. No longer do we have this skinny little, lean electron. And now it's this massive muon, which we don't know what it is. It just weighs more than an electron. And this exotic atom no longer has an electron going around it. And if you don't mention that, people are not in tune to what's out there, what these people are investigating, what these people have discovered and proved and whatever.
Yeah, but if I just want to know how gravity works, do I have to read all the ways that it doesn't?
Well, sometimes it helps for comparison. Okay, that's one issue. The other one is you got to look at it in a historical context. This is what we believed in. Well, it's like this is what we used to believe in, and now we're saying this is something else.
How do magnets work? And you go through the whole history.
Yeah.
Why?
Well, to say...
Grandpa, I got school in 2 minutes. Can you just give me the nuts and bolts version?
Well, you do get the nuts and bolts, but you kind of
2 hours.
It's like at the end you got to look at the needle in the haystack, because there's so much noise out there, and so you kind of have to.
Yeah, but I'm a kid that hasn't heard any other theory. Hey, Grandpa, how does magnets work? What would you say?
Well, here's how it works. Period. Yeah, you're right in that sense, but.
You'd spare little Timmy the whole history.
But let me tell you about the history. When we discovered lodestone, and then came Peregrinus and Peter Peregrinus, 13th century, and 1269, and he came up and he said, I know how a magnet works, and he wrote a letter to a friend. That's the first notion we have of positive and negative, the North and South Pole. People discussed about it, so he talked about it like, you know what I'm talking about, the positive, negative, North Pole, South Pole. And he said, hey, North Pole attracts South Pole, positive attracts negative. And positive rejects positive. He wrote a lot. He's the first guy who discovered that, Peter Peregrinus. And so it kind of makes you wonder, it's like, because we haven't evolved one iota from that. We're still saying, how does a magnet work? Well, let me tell you, positive attracts negative. Oh, there it is, I hope you can tell me which one is positive and which one is negative, because...
You gotta label them or else it...
Yeah, because... are they labeled? No, they're not. So, why do how does it do it? Very simple. Positive attracts negative. And so we haven't made any progress since the 13th century, at least, right? Positive attracts negative, North Pole attracts South Pole, and North Pole rejects North Pole, negative rejects negative, and that kind of thing, And people think they've explained it. That's the worst part, that people really believe that they have explained how magnets work. And that's the scary part, that people don't even understand that they haven't explained anything.
Today you wanted to talk about atomic structure, but I assume you're going to go through all the ways it isn't before we get the real atomic structure.
Well, not really. Today's a quick lesson.
Oh, yeah?
Today's a quick lesson. As far as I know, it's a quick lesson. And, we start, again, just to go over it, but very quickly. We go through the gluon, the fact that... and the reason I go through the gluon is the gluon is a special particle for me. I love the gluon because...
Should we start with the atom real quick?
No, I like to start.
What is a gluon?
I like to start with a gluon. Let me tell you why. Because a gluon is a particle, supposedly. It's a particle of standard model. I like to start with the gluon because the gluon has special properties that are of great concern to me. It's the poster boy. It's the kid on the carton. Missing kid on the carton or whatever. It's the poster boy for quantum mechanics, specifically for attraction. The gluon is a particle that pulls two quarks together. And I have a big problem with that because, first of all, on the one hand, You have the graviton. It's not part of the standard model because they can't make it work no matter what. And why? What can't they make? What can't they figure out about the graviton? How a graviton pulls. That's the bottom line. So it's not even part of the standard model. You know, they can't have it. They don't even have an equation for the graviton. But for the gluon, they have equations. And the gluon is supposed to be a little intermediary, a particle that mediates between two other particles and brings them together. And that's magical. Now that is magical. I mean, you know, quantum has two particles at the same location, or many particles at the same location. Okay, we're going to be discussing that. But it's got something more that's a lot more scarier than that, which is one particle at two locations. And that's given by the uncertainty principle by Heisenberg's, you know, indeterminacy principle. That's one. And the other one is that they have a particle that pulls. Now, if the particle looks like a hook, you know, here's my rope, I like to use that. And here, if it looks like that, if a particle looks like a hook, we can understand how. Right?
Like the sheep's cane when there's a bad actor on stage.
Right. You pull, you pull the guy out, the cane, you know. We can all understand a particle that has hook-shaped pulling on another one. So structure is important to understand that, because someone shows you two particles which are hook-shaped and they're pulling on each other. You say, okay, I understand. You know, I don't have to go to college to understand that. I say, okay, I understand why they pull or why they prevent the other guy from leaving or whatever, right? And that's the case of the gluon serving between two quarks. If the gluon can serve between two quarks, its architecture is very important. I want to know what the architecture is, because if they paint a picture of a gluon that looks like, you know, a hook, say, okay, I understand why it, you know, holds two quarks together. But that's not the case. The case is that the gluon is supposed to be like, you know, you're supposed to think of it as a ball. It's not a ball, but you're supposed to think of it as such, because all the particles in the standard model give you the notion that they're all balls. You know, in fact, they always represent them as dots, as circles, as spheres. They never give you the shape, the actual shape. And they say, well, we don't know what the actual shape is. Well, you better know if you're going to explain something in physical terms. If you're going to say, look, this gluon holds two atoms together, two quarks together, so then its shape is relevant.
Yeah, if you're going to explain something as fundamental as
attraction,
the reason for the pull,
right?
You can't just say it does and not talk about the structure. Unless you're just going to say, okay, these two the ball hits the other ball, and the second ball comes towards the first ball instead of away from it, like we normally know it.
Mathematically, you can do it, but physically, you can't. And that's the issue. If the guy can do it mathematically and can't do it physically, then mathematics is not the language of physics.
Well, I would argue you can't do it mathematically either.
Well, yeah, you put a negative. But they put a negative sign, and you can do it.
That's not doing math. That's doing magic.
No, because the magic part is the physical interpretation.
Yeah, but that's my point.
The mathematics says
if you put the negative there, you're cheating, because you're doing something that splits math and physics.
That's the point.
But at
that point, there's no relation between math and physics.
See, I don't mind math at any point if it's still within the laws of physics. If you're putting a negative sign that makes sense, that you can explain, then it's fair game.
And that's what I'm saying.
If you can't explain it, then you're just doing magic. You're splitting off and you're saying, oh, this is easier or whatever, or you can't think of the right equation that actually fits with what's going on. So they have all these ad hoc equations, kind of patchwork, filling in whatever they need to, just to get close enough.
Yeah, and the equations are one thing, but if they cannot be interpreted physically, then the equation is divorced from physics. And that's why I'm saying, mathematics is not the language of physics. The language of physics is objects.
We definitely need a mathematician on the channel to be able to kind of defend that side better.
Because like you said earlier, we do not need to cover something that isn't. So if we have the mathematician, we would have to say, look, shut up. because you know your stuff has nothing to do with
Yeah,
physics.
but if you're gonna talk about it anyway,
Yeah,
then we need
yeah,
the guy.
but that's
If we're not
the
gonna
point.
talk about it, then yeah, obviously we'll just talk
Yeah.
about our stuff. But if we're gonna talk about it, we need a guy who can actually defend it.
Yeah,
better than
yeah,
you can
I
with
guess.
because anything that you say, it sounds like a straw man argument. You're just pulling the gluon.
Yeah, but that's
out of
why
whatever.
that's why I pull their statements from
Yeah, but it might all
the
be
system.
out of context or some weird.
Yeah, that's for people to
rationale.
investigate. I'm trying to pull nothing out of context. I'm trying to make sure that people understand that this is what's out there. And you kind of need to go know what's out there before you can even get to the rope model. You know, you need to know what's out there.
Well, to be honest, I just want to see the guy kind of fumbling for words and trying to explain what he's actually doing. But that's just the that's just the evil side of me.
Anyways, getting back to the real quickly, this is what it's supposed to be. The gluon is supposed to, be thrown. I'll move aside here a little bit.
Well, but I wanted to first say, what is a gluon? Like what? We got an atom. Atom has a proton. Proton is made of
Three quarks.
and the quarks are held together by gluons.
Correct. It's a
That's
particle
all we need
that
to know.
that's all you need to know, really. The gluon is a little particle that holds quarks together. What are quarks? There's three quarks in every proton and neutron, and protons and neutrons form the nucleus of the atom. An electron supposedly buzzes around. Okay, that's the general picture that you will get from high school all the way to college, but in college it gets a little more complicated.
And we're talking about the smallest part of this whole shebang.
Those are the subatomic, the most important at least subatomic.
Well, subatomic we have protons, but subprotonic we have quarks, and subquarkic we have gluons, basically.
Kind of like that. The gluon is a little bead that is smaller than a quark, which is smaller than a neutron, or a proton, which is smaller than the atom. Essentially, it's like I give the analogy of the nail of the board that holds the boards to the walls of your house, which make up the house itself, right? So we're talking about the nails here, okay? And they claim they've seen the nails, or that they image them. You see it's called the star from this accelerator in New York. What is it, Brookhaven? And Brookhaven has supposedly imaged not only quarks from two gold atoms that collided, but the gluons. You see the traces of quarks and gluons, and you say, oh, you were able to image the traces of gluons? And if they say yes, then why don't you just put your little ruler across that gluon trace, and you'll know the diameter of a gluon. Very simple. You'll know how big a gluon is, and maybe even what it looks like. But see, all those images are phony. They're created by computers. They're not photographs, okay? And again, what the star shows, that explosion, is something dynamic. You're taking a picture of a movie, okay? And keep that in mind whenever you see that picture. But this is what a gluon is supposed to be. It's supposed to go between, the quarks, and keep them together inside the proton or the neutron. And maybe what they should have done there is put a little globe around the three quarks there, so that you understand that those three quarks make up a proton or a neutron, which are always pictured as spheres, okay? But you just think of that. Those three quarks make up a sphere, and they're held together by this little gluon, which doesn't allow them to leave the proton or the neutron, because otherwise you would ask the question, well, why is that the down quark and the up quark, why are they held together inside the nucleus or inside the proton or the neutron? And you say, why? What is keeping them there, and why don't they drift away? And what they've done is to explain that counter to what quantum mechanics proposes, is they've put a little spring. And so that's how they illustrate it. This comes from CERN. So this is not, this is not a straw man here. This comes out of CERN. CERN illustrates it like that. So it's a misleading image. They're putting a little spring there, and you say, well, I can understand why they don't go, drift away, because there's a spring holding them together. So is the glue on a spring? And again, how they explain that is that the more you try to stretch a quark out of there, the stronger force that you need, the more energy you need to pull it out. And so what they've come up with is this, this image of where two quarks being pulled out, one farther and farther away from another, produces another quark or anti-quark between them. And that quark or anti-quark essentially is being built by gluons.
Why are we going through gluons again?
Well, it's always it's always and again, the gluon is the poster boy for quantum mechanics, because they cannot explain the force of pull, and they're getting away with murder here when they put these bed springs. So I always like to begin my presentations of quantum with those bed springs, because that is the poster boy of quantum mechanics, the gluon. It's cheating, it's lying, it's not what a gluon is supposed to be. So so that leads us to the standard model. Standard model looks like that, and you can see the little gluon there, upper right hand corner, the little G there, gluon in orange color. Okay, and it holds those quarks together on the left hand side, the violet ones. Okay, and so there's 17 particles. That's the foundation. That's already quite complex. The Greeks had what, 5 elements. Ether was kind of iffy, but they put that in there. Like there's 4 for sure, but there's this 5th one, the ether, which we haven't proven yet, right? So there were,
It's like
and
the
here,
graviton.
And here we have these 17 that have been proven, but you can't see the graviton in there because it hasn't been proven. That's hypothetical, okay? And so is the tachyon and some of the others. But then, it gets a lot more complex because they've had, all this other, all these other particles like the quasi particles we went over the other day, and those particles that make up, the exotic atoms and so on. So it gets quite complex. So at some point you have to ask the question, what does an atom look like? And for this, I'm sorry, son, but we got to go through a little history, and the history is not too lengthy. It just starts essentially at the turn up to the 20th century, and we have Mr. Planck, Max Planck. He came up with a quantum, and from there, you had other people saying, okay, we're getting to the nitty gritty here.
Wait, he came up with the quantum?
Yeah, he came up with a quantum through a black box radiation, but that's a long story. But the point is, he said, there's a quantum, a quantity of energy, and that quantity of energy is going to become, morph into the photon. That's going to be the particle of light. But when you say, well, what do you mean particle? Are you talking about a corpuscle? No, we're talking about a quantum of energy, and they called that the quantum. And many of them are quantas, plural, okay? And so you say, well, what does an atom look like? And that's what they were trying to get to. Why? Because you had people like, the older folk. What was his name? I forgot the guy who was running the lab there in England, in London, and I got him on the tip of my tongue. Anyways, he came up with with a different model. You had the plum pudding model. Yeah, that's what it was. It's called or known as today, which had all these electrons put into this cake. You had the plum pudding. You had the little and negative charges fit in there. And that's about the time when Bohr came along and Rutherford, and they started doing experiments at the atomic and subatomic level, smashing particles and so on. And they said, look, we come up with a different model. And Bohr came up with a planetary model. And people today in quantum laugh at when you say, the planetary model, and they say, you're raising a straw man. It is not a straw man. It is not a straw man. I want to make that point today. The planetary model is not a straw man, but they'll say it is. And let me tell you where the discrepancy is, why they're saying it's not. Because when you go to high school, they say, look, what does an atom look like? And they show you a ball. We're talking about the hydrogen atom, the most basic atom. They show you a ball, which is the proton in the center, and they show you, you know, an electron going around it. And they say, that's not our atom. That's the planetary atom. That's Bohr's model, and that's obsolete. We don't do that anymore. You know, I mean, we laugh at that. You say, oh, I thought that was the model, because that's what you see all over the internet. You see the planetary model. You say, no, we have the more advanced quantum model. And you say, oh, quantum model. That must be something, you know, I probably have to get a PhD to understand what that looks like. And I want to show you don't. Okay, there's no difference between the planetary model and what they use today. They do use the planetary model, and that's the second or the third point, I guess, right now, where they mislead you. One is gluons attract. That's nonsense. They put a bed spring. The other one is, you know, according to the Heisenberg indeterminacy principle or uncertainty principle, two particles can be at one location or many at one location, superimposition. But then worse than that, more irrational, is one particle can be at two places at once. It's distributed. It's a field. And you say, well, what are you talking about here? You know, and so, but here's the other one, and that's the you know, what an atom looks like. And like we said yesterday, because of the wave function, they came up with these orbitals. Okay, so let's put that up there, and here are the orbitals. These are the different orbitals for hydrogen. The shiny parts that you see there are where the electron bead, the little dot, is likely to be found. And the darker areas, the cooler areas, you could say, you know, is where there's a lower probability of finding the electron. These guys are concerned where they're going to find the bead. That's what the equation, the Schrodinger equation, that's what it deals with. Where is the electron? Not what it looks like, but where is it? Okay, so they're talking about where. They're talking about coordinates. They're talking about, you know, length, longitude, latitude, and altitude, that kind of thing. Okay, that's what Schrodinger's equation deals with. And okay, so those are the different orbitals that you can imagine. If you run Schrodinger's equation. Those are energy levels, and these energy levels convert into orbitals. So far, so good. You can call them whatever you want. You can call them X if you want, as long as, you know, you realize that you're talking about a volume, a region of space around an atom. No problem up to that point. The problem is when you start merging these and creating not only higher or more massive elements, but when you also convert them into molecules. When you get you know, a hydrogen with carbon, for example, and you start merging the orbitals. The orbital is not supposed to be a physical entity. The orbital is just a region where you can find the electron bead. Well, they forget about the electron bead, and they start merging the orbitals and saying the orbitals are keeping two atoms together. That's when it comes, you know, very funny. And, you know, here's the equation, Schrodinger's equation. And if you put variables in there, you end up with those. If you put numbers into those variables, you'll end up with these orbitals, right? And what do they look like? Well, they look like something like this. Okay, here you see a picture of the orbitals. Okay, and so up to that point, we have no problem as long as you don't treat them as balloons, as tunnels, or as structures. You say, look, in that region, in that globular or orbital region, you can find the electron bead. Up to that point, we have no problem. Where do we have a problem? We have a problem when you start merging them, like here. You see the carbon orbitals merging and forming, you know, in this case, two carbon atoms, C2, okay, two Cs. The orbitals are merging. And you can even say, look, I have no problem with two orbitals merging. You know, the two regions, they overlap, no problem. The problem is these people are saying that the orbitals hold two atoms together. And here you see another image, and this one is, methane. You have 4 hydrogen atoms, and they're going to fit into the p orbitals of the carbon atom, okay? Here it gets very scary because the hydrogen atoms are held together in this molecule because the orbitals overlap, and the orbitals are treated as physical entities. It's like, two balloons merged. And yes, we're saying that, the model of, the rope model of the hydrogen atom and of all atoms in general has to do with balloons. We are talking about balloons, and that's what they illustrate. But they don't call them balloons. They call them orbitals, and they say, the orbital is not a physical entity. It's where you can find the electron bead. So it's a very circular argument for them. You just go over and over that stuff. Okay, so what does the atom look like? This is what you'll see out there. You'll see this description. Bohr's planetary model says Bohr suggested that instead of buzzing randomly around the nucleus, electrons inhabit orbits situated at fixed distance away from the nucleus. That's the key point. The key point is that for Bohr's planetary model, the electron just goes around orbits like the Earth around the sun, but it orbits at a fixed distance. That was his key point. And they replaced that with what is called the quantum model or the cloud model in around 1926, 1927 thereabouts, by the Fifth Savoy Conference in Belgium. And they said, and this is the description today, however, the model was misleading in several ways and ultimately destined for failure. So they got rid of the Bohr's planetary model, and that's how they get rid of you when you say, oh, but yours is a planetary model. No, they say, no, ours is different. The maturing field of quantum mechanics revealed that it was impossible to know an electron's position and velocity simultaneously. That was Heisenberg's uncertainty principle. Bohr's well-defined orbits were replaced with probability clouds, where an electron is likely to be. So we still have the planetary model, but it's not the planetary model with a fixed orbit and the electron rolling around it, at a constant rate. That's what they're saying that has been replaced. What did they replace it with? They replaced it with the electron bead still orbiting the nucleus, but now it's not orbiting first at a fixed distance. It changes distances, and it can be found anywhere in a region around the nucleus. So it's still a planetary model in the sense that these are two discrete particles, the proton and the electron. And their only concern here is that the equations tell them, Schrodinger's equation that you saw a minute ago there, shows that the electron bead can be found in irregular locations in a region around the proton. That's all there is. It's still a planetary model in the sense that, it's not orbiting at a fixed rate and at a fixed distance, but it can be still found around, bouncing around a region
it's
around
still a ball next to a ball.
Correct. Proton ball, bowling ball, which is, accompanied by an electron bead. And the question there again comes to the force of pull or attachment or tug, any drawing, like drawing a drawer, any of those words that you want to use. In other words, why doesn't the electron bead fly away? What keeps it bound to the proton? And that's where you enter with quantum field theory. They use the field to explain these things, the magical field.
Why doesn't it fly away and why doesn't it go to the center? It's two questions.
Yeah, okay, that's another one, because the issue also is why doesn't, especially, with these orbitals, where was it? Here, the orbitals. Here's the orbital, right? And those are p orbitals that you're seeing, the first ones, then you get to the s and the d's and higher level orbitals. But the first one is the s orbital, which is that one there, the round one. And then those that are coming in there, those elongated balloons, those are the p orbitals. And the question is, when the electron goes through that p orbital and gets close to the nucleus of the atom, why doesn't the proton suck it in? I mean, positive attracts negative, right? Well, they try to keep it at a distance. But it turns out that, that electron goes all the way to the other side, to the p orbital that's exactly, along the, like in this case, the x-axis or the y-axis or the z-axis. It goes to the other orbital. And you say, well, how did it go through the center of the nucleus? How did it go through a proton that's positive? And they say, well, it doesn't. It just jumps. It kind of appears on the other side. And so again, they have all this magic, all these magical explanations how the bead ends up on the other side, how this bead is being pulled by the proton, but it doesn't fall into the nucleus. It just kind of jumps and goes to the other side, to the other to the other part of the figure 8, p orbital. And so they cheat. They cheat in so many ways from a physical point of view that you start wondering, look, does mathematics really, is it the language of physics? Because mathematically you may be able to describe this, but you haven't been able to explain it, how that applies to physics, the physical aspect, the physical interpretation. And that's when they say, well, we don't know how Mother Nature does all these tricks. We can't explain it. For that, you got to go to see the philosophers of science, the philosophers of physics on the other side of campus, which don't know either, by the way. These people don't know either. They're waiting for the physicists to tell them, the mathematical physicists. So we don't know. There's no communication today between the public and these mathematicians, because the public keeps asking questions that relate to the qualitative aspects or nature of the atom, and these people just give you a runaround. They say, look, you got to take a course in college in order to understand what I'm talking about, and you don't, because this is the way you should be able to explain it right there. When you look at these orbitals, you say, okay, explain that. This is what you illustrate, explain that, and they can't explain that. They just put these balloons there and they say these are orbitals where you can find a bead. And if the bead is a negative and the center of that whole shebang is positive, why doesn't, when the bead goes close to it, why doesn't it get sucked in? And they say, well, no, because it jumps to the other side. By what? By magic, teleportation, or who knows why. You'll never know. They say it tunnels through. And so this is part of the problem. And so here's the image of a atom today. But this is the atom. This is Bohr's atom. You can see they're fixed. These are fixed orbitals. You can see that all the atoms are going around a specific orbit, okay? And they're saying, look, you're raising a straw man. This is not our atom. This was Bohr's atom. We laugh at it today, okay? Oh, okay, so what did you replace it with? And this is where you really want to laugh, because they replaced it with this. This is the cloud model of the hydrogen atom. All these bees buzzing around a nucleus. So now the hydrogen atom has only one electron. What are all those little dots there? Well, those are the electrons that are everywhere at the same time. Okay, so you have one electron there that's spinning around, okay? That's how it's supposed to be, and they replaced this with the cloud model. This is the actual atom that is used in quantum today. This thing that you're staring at right there.
So they added more dots.
They added all these dots, and they're saying,
that's all that's changed.
Yeah, what they're saying is, look, Schrodinger's equation tells us that the electron can be at many places, but not only at many places, it can be at many places at the same time, according to Heisenberg's uncertainty principle.
It's actually true. A balloon can be at two places
Yeah.
at once.
Yeah, if it's a balloon, yeah. But they're not saying it's a balloon.
I am at two places at once, technically. One shoulder and the other shoulder at two different locations, and it's both still me.
Yeah, but if you're talking about a little bead that like if you take one point on your body, right?
Yeah.
Any point that you want, say or you call it an atom. Okay, so we say this atom makes up you, right?
Yeah.
My son Hans, Adrian. Right?
It's
So we have one atom. So that specific hydrogen atom is everywhere at once. It's not like we have not like he's made of a gazillion atoms. They're saying that one atom in this case, right, is his whole body is made out of that one atom. And you say, how can it be made out of that one atom? Well, because that same atom can be everywhere at once.
Because what they're really saying
So he's made out of only one atom.
Because what I said is that an object in any shape can be at two locations at once, because you just take one location on the object and another location on the object. But they're saying the center of the object, let's take the hydrogen atom that you just talked about, the center of that atom is in two places at once. See, now you can't do that anymore because there's only one center.
Not the center, but
that's essentially what they're saying.
Why? Why are you saying the center?
Because you're not saying that the atom takes up room that you can call two locations. You're saying that same atom, the center itself, and I mean the whole thing, obviously, but let's just focus on the center. They're saying that center is two places at once.
In the case of you being made of that atom, that's what you're talking. Yeah, okay. It's like I'm made out of a single atom. That's what they're saying. This is the analogy. Okay, I'm made up of only one atom. You say, well, I thought an atom was a little thing like this, a little dot, and you say, yeah, it is a dot.
It's in a lot of
well, how come I can see you all over the place? They're saying because that dot can be everywhere at once. It's just one atom, but it's everywhere at once and makes up me.
You're a hologram.
So I'm only made out of one atom. That's essentially what they're saying in as an analogy for their atom, for the cloud model, the quantum model of the atom. The official. This is the official one. Okay, there's no scarecrow here. I'm not raising a straw man here. What we're saying here is that you have a proton, and you have all these bees. And let me put that up there one more time. Here.
Yeah, it's not enough just to say that there's that many electrons. They have to say it's one electron doing all that.
Yeah, they're saying, see all those little bees that you see buzzing around there?
That's all one.
That's one. See, here you have the one electron.
No, hold on.
This is the one electron.
Four orbitals, so there's four.
Yeah, right? No, because those orbitals also represent the different orbitals that hydrogen can have. Remember, here you have the, where was it? Let's see if I can get it. Orbitals. No, yeah, I think it's this one. Well, not really. That's not the one I wanted to show. I wanted to show the hydrogen or here. Hold it. Let me get that thought in there.
Yeah, but I thought there was only one electron per orbital.
Yeah, but look. This is the hydrogen. What you're seeing there on the right hand side. Maybe I can make it bigger so that we look at the picture.
You're putting a lot of pictures up. I don't know which one you're talking about.
Well, let's get this picture right here. Let me make this bigger so we can see it right, okay? Don't look at me, look at the picture, okay? And what are we saying? See those hydrogen? All those are hydrogen, but they're different orbitals. These are electron orbitals.
These are different types of hydrogen. Let's just take one of them, right? Let's take the third one.
No, it's if you apply, let's understand what we're looking at there. We're saying that if we apply Schrodinger's equation, right? And we run, different numbers into the variable. We punch in different numbers into the variables. You're going to end up with all these different kinds of orbitals.
Okay, but that's different. I'm saying if you just take one hydrogen atom, right? It's one of these. Right?
Yeah, but it's all of them.
But it's not all of them. It's one of these.
No, it's all of them. That's the point.
Isn't it just one of these?
No, you see all those three values. Listen. All those three values that you see, can you see those three values?
Yeah.
Okay, the three values that you see there, think of them as radius, or just think of them as latitude, longitude, and altitude. Altitude from the center of the atom, okay? So we have latitude, altitude, and longitude, latitude, and altitude, right? Those are the three numbers there. You can think of them that way, okay? And if you put numbers into Schrodinger's equation, you're going to end up with all these different orbitals, which means that those are the different probability distributions where you can find, of locations where you can find the electron around the proton in a hydrogen atom. And so they all exist kind of simultaneously, superimposed upon each other. That's how...
So why did they show
that's how
so many...
they're saying if you have 0, 0, 0, you get this. If you get a 0, 0, 1, you get that. If you get a 0, 1, 1, yeah, but they're superimposed.
But it's then why not just show one with all of them?
Because these are again the probability distributions which can be superimposed one upon each other. You're supposed to think of these as simultaneous.
They all are. Get that,
they're all like components.
Why not just put them all on top of each other?
Well, this is just a mathematical calculation to show you. If you apply Schrodinger's equation, this is what you would get for the 001, 00011, 111, and so on down the line. Okay, it's like if you replace altitude, longitude, and latitude. numbers for them, that's what you would get. That's essentially what they're saying. But anyways, the point is that this is the atom that you see today illustrated. You see all these little balls. The blue balls are supposed to be the electron beads, and they're buzzing around a nucleus. Okay. Here's the French atom. I like this one because French show this to their folk over there in France. They show this planetary atom. They're still in the, I guess, into the 20th century, early 20th century. They explain electricity as the flow of electron beads, and they show three quarks, as you can see, make up one proton and one neutron, and you can see they show them as balls, and the electron is a bead that goes around. Okay, it's a planetary model, but the only change that they've made today, or since 1926 or thereabouts, is that the electron bead is no longer orbiting at a fixed distance and at a fixed rate. It can be anywhere, and it jumps around from one place to another for no reason whatsoever. It just magically appears on the other side of the atom, because that's where they measure, and they say, oh, we found it over here now, and now we found it over there, and then you say, okay, the electron just bounces around, we don't know why. And if you think of the electron as a balloon, then you have no problem understanding, because you say, okay, I can see that if the balloon encapsulates the nucleus, then I can see why the electron, if I touch the balloon on one side, I'm going to measure it there, and if I touch on the other side, I'm going to measure it over there, and it's simultaneous because the balloon encapsulates the entire proton or the entire nucleus. So then you can understand it with balloons. You cannot understand it with discrete beads. That's the key issue here. Okay, so here's our model. My son wants me to get to our model, and here's our model of.
Oh, we finally started.
Yeah. We start now the show. Okay, this is the model that we started yesterday. Essentially, it's the radius, latitude, and longitude. That's what they've been describing. We get rid of the axis. We don't need that. And when we apply Schrodinger's equation, all we're doing is pinpointing one point, one location on the surface of the electron shell, electron balloon, that encapsulates the proton dandelion. We have a little dandelion there in the center, and all those rays are pointing in the direction of every atom in the universe. Okay. In other words, the ropes come into the shell of an atom, to the cloud part that encapsulates the proton, and that's where the ropes fork out. One rope goes around and forms the electron shell. The other one continues, one thread, goes around and encapsulates the proton dandelion, and the other one goes to the center and forms the proton dandelion. And that's all there is in the universe, just atoms made of the ropes that are going to be the mediators of light and gravity. Okay? And so let's look at our model. Let's look at model in a little more detail so that you understand it. Here's the rope model of light and the atom. It's also of gravity. Here we have two atoms bound by an electromagnetic rope, and they torque the rope. They send a signal along that rope there. It's a torsion signal. The signal travels in both directions simultaneously, because when you torque a rope, like if you torque your grandmother's rope where she hangs her clothes, if it's tight enough, you'll see that you don't know which direction the signals are going, the torsion is going. It's going in both ways.
If you torque it in the middle.
No, you can torque it at one end, but at the same time that you're torquing, you don't know if that, it's not that it's going outwards, it's just twirling in place. It gives you the misleading impression that the goosebumps are moving in one direction, but they're really going in both directions at the same time. That's the funny thing about a rope. Just twirl it anywhere, because the whole rope twirls, right? You got to think of this as a very tightly pulled entity, right? It's stretched to maximum. That's why light has a constant speed. And if you torque the rope, the signal travels in both directions to both atoms. Okay, and that's the funny part about this.
Yeah, I think everyone's going to have to do that at home to really understand or come to grips with all the physical properties
Yeah.
that a rope actually possesses.
It's not.
How does a rope actually? Because no one really.
It's a little
really
bit
deals with
counterintuitive
ropes.
until.
It's not. That's the thing. It's weird because no one really deals with intertwined ropes daily.
Right.
On the daily. But
Yeah.
if you were to take a rope and just kind of play around with it, see everything that an intertwined rope like this, all the things that it does. When you do this, it does that. When you do that, it does this. You kind of get a better grasp on the model of that light could be explained with better than just balls.
And the mathematicians will have to change their focus. Instead of dealing with particles, now they're going to have to create mathematics to describe all the things related to torsions and ropes. And and that's going to be another monster. And they're going to have to apply Schrodinger's equation now to the balloon. The balloon that they've been describing for years now is a true balloon. It's a true cloud in that sense. Not because you can find an electron bead in there, but because the famous orbitals are really a physical balloon that encapsulates each atom. Otherwise, you're made out of motion. They're saying what are you made out of? Well, I'm made out of vibrations. That doesn't work. Well, you're made out of balloons, and it's the balloon that vibrates. You can't say that you're made out of vibrations, out of verbs, and that's essentially what quantum says. Okay, so that's the big picture. Let's look at a little more detailed version. Here you see the proton dandelion in the center. You have all the rays coming to it. It's a little star or a little dandelion or a little rolled up porcupine. Okay, and you have the electron shell. You have the ropes coming, forking at the electron shell. The blue one, we'll call it the electric thread, goes to the center of the atom, forms the proton, and the red one goes around and forms the electron shell. This is the model we're proposing for the atom. We're saying an atom, this is a cross section, by the way. It's a 2D version of the atom. But what you see here is that all the rays converge on a center, and these rays are actually threads. It's a thread, a physical thread, so tiny that we can't see it, so thin that we can't see it. And so what you have is the rope coming there to the electron shell. The red one, the magnetic thread we call it, just to keep with convention, goes around, forms the electron shell, balloon, cloud, whatever you want to call that, and it encapsulates the proton dandelion.
That zoom in is really nice.
Yeah, so, and by the way, we have to give credit here to Mr. Dave Robinson. He put this model, he came up with this very good version of the atom that he put in, in the Prezi presentations forum, or what is it? I'm not sure what Prezi is, a platform or whatever. Anyways, their site, the Prezi site, and he put this atom, and I borrowed, stole it from him. I give him credit all the time. This is a good version, and what I've done is just use that to come up with what you're seeing there. But essentially what you're looking at is a cross section of the hydrogen atom. This is the simplest atom. Here's the H atom, center, that's the proton, and all those threads, the blue threads, are coming from every atom in the universe through those ropes, and they fork at the electron shell, which is that red, I'll call it the magnetic thread that goes around and encapsulates the proton.
We definitely have to go into larger atoms at some point, like the helium atom, just to get an idea of how a bigger atom would look.
Yeah, it's
but
a monster.
Because you always only deal with the hydrogen, but just the helium.
Yeah,
just one other one would be nice, just to see if it's even feasible with bigger things.
Yeah, and it is. I've already pictured that, but yeah, drawing that. Maybe I need another Dave Robinson there to.
We don't need the uranium one.
92.
Yeah, well,
I don't think so.
Helium
no, but,
is good.
But maybe I can get Dave to do helium atom, or maybe Daniel Ferguson there. He likes to do drawings, so maybe they can work on a helium atom. That would really help a lot, because they like to do drawings, and this was pretty good, I thought, So this is a pretty good image, a two-dimensional image of the rope model of the atom. let's go one step further. So we look at the construction of this, okay? So we can see how it's constructed, okay? And again, what we have is the electric and magnetic thread, no longer fields. Field is a concept, and people don't understand that. They just, a lot of people say, oh, all you did was just replace the word field with the word thread. There's a difference between a field and a thread, and people don't understand that. That's why they're not physicists. A field is a concept. It's just saying there's a value at each point in space in this region. That's all they're saying. And, when they say, like Maxwell, he said, light is comprised of a electric and a magnetic field. He got that word from Faraday. And what did Faraday mean by field? Well, he says, there's something in this region which I don't understand. I'll call that a field. And people now have turned this field after, 200 years. They say, oh, yeah, I know what a field is. Oh, what is it? It's a concept. Field is a concept. It just says a value at each point in space. That's how the word field has evolved. So you can't use the word field in physics or in science.
And what's a thread?
A thread is what your grandmother sews with. That's a thread. In other words, what we're talking about, we're saying that there's a physical thread that binds two atoms. And these two threads are twined, and that's what light is going to be. Light is a torsion along those twined threads. That's essentially the atom that we're talking about. Or the light,
But there's no such thing as a difference between, or is there a difference between the two threads that make up a rope? Is one red and one blue?
No, absolutely. There's no difference. We're just trying to keep with convention. And we're going to call the magnetic thread the one that forms the electron shell. And we're going to call the proton, dandelion, that's going to be the electric thread. But that's just to keep with convention only. Okay.
Yeah, but I think it would also be helpful to have this same picture all in the same color, because that's more realistic.
Yeah, but see if you
okay. Yeah, I know it helps, but I'm just saying if you want to see the realistic version, it's all the same thing. Which is weird to think about.
Okay,
in my head, I'm always thinking about it like two different threads, with different properties.
No, they're not.
This thread
they do.
Out, and
they
this
do
thread
have
goes to the center, but it's really the same material.
It's the same material. It's one thread. The underlying hypothesis: there's a single thread in the entire universe.
I guess the question becomes how do they choose which one goes around and which one goes to the center?
Yeah, and there isn't. What we're saying is,
does one thread talk to the other one? Hey, buddy, I'm going around. You're going to the center this time.
Yeah, and again, we don't make any distinction. We're just saying, look, just to be able to explain, right? We're just going to separate them because the magnetic thread is what we're going to use for magnetism. That's the only difference.
But it's still a legitimate question. How does...
And it doesn't. No, it could be any of the two. It could be any of the two.
Why don't they both go around? That would be the question.
And they do. Remember we came up with the fact that they both go around?
No, that's with magnetism. I'm talking about the electron shell.
Again, it could be either one.
Why don't they both go to the center?
That's just the way it is. I mean,
but the legitimate question becomes: how do they choose which one goes around, which one goes to the center? That's a legitimate question.
No, it's not. It's not a legit. It's just there is no choice in the sense that
why don't they both happen to go to the center?
One goes around, the other one goes straight.
Yeah, but which one?
But that's that's just the way Mother Nature is.
No. There's a question there.
There is no question because
you're saying it's just like
it
that,
just
but that's
is because
question.
One goes around, the other one goes to the center because that's the way the atom is. It's like saying, why do they twine? It's just the way it is. I mean, they do twine. And it's not like you can say, why do they twine?
That one goes to the center, one goes around, but the question becomes, how do they decide? What's the pecking order? What's the physical mechanism that makes one split off to the top and one to the center and not the other way around, or both to the center or both around? Like, what's actually going on in at the electron shell?
Yeah,
why A not B? That would be the question. If they're the same material.
They are the same material.
So there's an actual question there.
Well, I don't know. I can say only that one goes around, the other one goes straight.
But at least
why it goes?
At least you say I don't know sometimes.
Yeah. There is no. I'm not sure if it's a valid question. It is to some degree, maybe, but maybe it's not because again, it's like asking why do they twine to begin with? Hold it. Let me finish. Why do they twine to begin with? Well, that's just the way it is. There is no why.
Because the
answer to that question is because God decided to.
That's not one of those. Yeah. Because with twining you don't need priority. You don't need one before the other or any
But
of
you
that.
can ask
They're-
that
they're
question.
simultaneous.
But you can ask the
No,
same
you can
question.
ask any question, but,
Yeah,
I'm
but-
saying there are some questions that fall under the that's why it is, that's how it is, but this isn't one of them. Because
Well, I
you
don't know.
actually have to say why A and not B and why B not A.
They fork.
Yeah, but
They
why does
hold it,
one go to
hold
the
it,
center?
hold it. They fork. They fork, and that's the way God decided. That's the way Mother Nature decided that they should fork.
Not that they should fork.
That they do fork.
Not
That
that
they
they
do
do
fork,
fork.
like
Not
they
that
do
they do
twine.
fork.
They
Not that
twine
they
like
do,
they do.
Not
fork.
that they do fork. It's how they fork.
Yeah, it's how they fork, how they twine.
Not how they twine, because we have to know why. How does B know to go around or not to the center? Why don't they accidentally like trip up sometimes? And
Because
go, oh, you were going
because
to the
you're
center,
asking
not
a
B."
question of purpose again,
Not
a reason.
purpose, not purpose, because they both fork. We get that, but how does A always know to go to the center?
Well, that's the point. The point is that it's not like A or the electric thread knows, oh, I'm the electric thread. I'm going to go to the center, and you are the magnetic. You're going to go around. It's like one will go here, and the other one will go there. It's like they fork out because I guess I would think that what happens is you have this shell, and you have this rope converging upon the shell. And at that point, it doesn't. Both of them just don't go through because, again, that would be a neutron. My neutron is convergence of ropes. But when you have the atom itself, the hydrogen atom, one goes around, and that's just the way it is. And he asks, well, how does one thread decide to go around, the other one go straight? It's not like they decide. One will go straight, and the other one will go around. How you can say that they decide? There is no decision.
Yeah,
one goes this way, and the other one goes that way. They fork out,
But
the forking is like the twining. The way I look at it is, why do they twine? Well, that's an irrelevant question. They do twine, and why do they fork? They do fork, fork means one's going to go this way and the other one's go that way. That's all. It's not like, do they decide that? Do they have intelligence?
There's a priority there, because if we're forking, if you're going that way and I'm going this way, now one has to go before the other. When they're twining, it's
you're asking a question.
Does the one that goes to the center, like, does one just happen to be more aligned towards the center? And
nothing like that.
There's no difference between the one that goes in.
There's no difference between them. It's like they fork. They fork at the electron shell. We have to concede that they fork.
Yeah, that's not.
And that's God's decision. That's Mother Nature who decided that they fork. And if they fork,
does one go? Like, is there like a priority thing where the one that goes to the center goes first, and then the other one has no choice but to go around? Is it something like that? But that's something we have to talk about in another one.
Okay, well, we'll fight that out in the kitchen. We do a lot of fighting here. But anyways, let me finish up with the last picture here that I have, and that's the quantum jump, and how the fact that the quantum jump torques the rope. Okay, what it does is, by quantum jumping, which is this pumping that the atom does. And that's the quantum jump that Bohr discovered, was it, I think 1911. And what it does is torque the rope. That's what it does. That's the cause of light. That's what triggers the rope to torque. That's the torsion that's moving along the rope, or the one we perceive as light at the end of the rope, okay? Anyways, that's the model, and that model contrasts with the quantum model that says, you have beads going around, and those beads used to be electron beads. Now they could be muon beads and pion beads if you're talking about exotic atoms. So they made a big mess, and they also created countless particles that, form the center of the atom. In other words, there's more than protons and neutrons in a nucleus. What you have is also, those are broken up into quarks, and those are mediated by gluons, and then you have, coming out of there somehow, because it comes out of the atoms. You have muons coming out of there, pions coming out of there. You've got all kinds of particles, 200 particles, neutrinos, everything comes out of that atom. And so all those little particles that they've discovered are inside that atom. So you're not only talking about an electron orbiting a proton anymore. No, now the proton's broken up into countless particles, and there's up to 200 particles that they have come up with today, including, the quasi particles. And so, with that, we'll see you tomorrow, and we're going to continue with a comparison of the quantum model against the rope model of quantum mechanics. The rope model, against quantum mechanics. So we'll see you tomorrow, guys. Same time, same station. See you then. Bye-bye.